This, as you can see, that closest to the Ronda Ring, which connect between the radial highway Barcelona from the north of the city and the Ronda Ring. So it shows that the crossing of the two main highways between the Augusta and Ronda de Dalt and so-called RJ branch in the dash line. So the first section is indicated by this black shaded area. So this tunnel is functioned to connect between these two sections area from the Augusta and also the Borràs Square. Okay. Again, before we can have some back analysis study, we need to get the soil profile information. So uh, it was reported from the few borings and the when at the site they were around 1, 2, 3, 5 bore that shown on the soil profile informations. So the soil profile informations as stated here, um, the tunnel actually being excavated that closely to the Bollock 5, SBR5, SBR1 to SBR2. So it was founded that the metropolitan Barcelona area consists of ancient quaternary soils, describe a sequence of reddish clays and yellowish silt with variable proportions of gravel and some carbonatic crust. So these are the steep deposit which whose thickness decreases toward the north in the directions of the cholesterol. So not to forget, since our soils originated from the rocks, so it explained here the parent rock, how the parent rock that stand to the failed area. So it says also the steep deposit thickness decreases towards the north in the directions of cholesterol mountain range, which act as a natural limit for the city. So the tunnel is located in the northern part of the city where the quaternary deposit progressively thinner overlay the rock substratum, decomposed granite, shales, and metamorphic rocks. So the RJ tunnel is interpreted from the boring as shown here. Later I will show you. Um, it also from this product number SPR3, SPR2, SPR1, and also SPR5, the tunnel is positioned near to the SPR2 and also SPR1. So these figures indicate to you the longitudinal geotechnical profile along the tunnel as well as SPTN number. So as shown here, the formations of the field area consist of some field gravel with locally carbonated clay sand, and decomposed granite. So decomposed granite at located below or the bottom from or we call it as a stratum base. So the problem occurred when they could not identify the closely what were the soil type near to the SPR2 bollock and SPR1 bollock. So it also mentioned that the tunnel was entirely excavated in quaternary soils, granite substratum close to the invert. So the soil at the location SPR2 was described as a sequence clearly gravels, carbonated clays, and clay gravel grains, uh, and also clay sand, and finally the granitic substratum. So it was founded that the decomposed granite is located some far below from the ground surface. And here, the presence of some fields difficult to identify because they were also described as clay and gravel. So the profile of the soil near to the collapsed tunnel as shown in this bollock SPR3, 2, 1, and also 5. So these are the informations related to the soil profile and the originated soil in the field area. So what's the important keys when you are planning to construct tunnel, mostly tunnel excavations? We need to understand the weakness plane of the rock itself because we want to have some tunnel excavation that not in parallel to the weakness plane because that are triggering to the most catastrophic failure. So in part of the design of or in part of the constructions of the tunnel itself, we need to identify the best directions that we can start doing the excavation of this tunnel. Okay, this is the important from the soil bollock report. So there are few construction phases related to these excavations or related to the constructions phase for this kind of the tunnel. So the first phase construction involved with the build manually in classical head and bench excavations. So if you have this note, then please look at to the figure 7.3. The figures 7.3 as shown in here, as you can see, there are two stages. The first one to excavate at the head of this tunnel, and then the second phase to construct a bench of this tunnel. So it was started by having this kind of the cross sections, and you can see that the head was excavated ahead of the bench, approximately 12 meter, and was excavated in full in unsupported length of 1.08 meter, and was immediately protected by heavy double T wide wing HEB 160 steel sets, perforated steel banner plates supported by the sets completed, and the steel reinforcement of the bulb. So as we look at here, the cross sections of the tunnel excavation seemsly perfect because it was protected by some steel reinforcement and any other kinds of the structure. The concrete was pumped between the burner plates and the excavated soil surface to form a continuous monolithic lining, 25 centimeter thick. So the wire mesh and chocolate layer 6 meter thick were finally applied. So in this figure 7.3 also shows the lining were installed to support the constructed of the excavated tunnel, and 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 in order to have some more reinforcement, daily advance or two to three steel sets were installed at the cross sections or at the tunnel face. So you can see from this figure 7.3, there's some schematic diagram indicates the dimensions and the head length distance from the top ground surface to the locations that we started to have the first stage of the tunnel excavations. And the diameter of the tunnel curve or tunnel arch is around 4 meters. Okay, the second construction phase involved the excavations of the bench. So the cross section had a width of 8.4 meter and height of 2.3 meter. So a critical operations of this phase was appreciate underpinning of the valve. So the underpinning is the process to strengthen on the structure's foundations. So to do so, the sets were lengthened by means of straight and vertical HEB steel reinforcement or steel set. So the same support when a place pour mesh concrete and finer shotcrete layer were also applied on the tunnel excavated. So the next figure 7.5, figure 0.5. So this is the real condition showing to you what are the meanings of perforated panel plates, plates between the steel sets and also skin reinforcement. So this is the image shown in the raw constructed tunnel on sites before having the concrete lining or spraying. So back to here. The valve was therefore thereafter supported by two longitudinal soil buttresses with the approximate dimension indicated in the next figure. So right and left buttresses, however, had an offset distance which ranged between 4 and 12 meter. The specifications require that the valve should be underpinned by excavating the buttress in width not exceeding 2.60 meter with two new vertical posts added. So the buttresses is one of the type for slope protections or to retain slope or to retain soil from any kind of movement. So this is that indicates to you the meaning of buttress. And this is the final schematic of the tunnel excavated by having the buttresses with a width of 1.75 meter with a height 2.50 meter. Okay, how the failure occurred. So it was occurred around that particular year, 1991, and the collapse destroyed in length of 11 meter tunnel, which was being finalized ahead of a fully supported section. So the next figure 7.7, okay, the figure 7.7 is actually shown to you, and the finished tunnel that collapsed at the particular area. So the section is located at the opposite extreme of the photograph, which was taken a few days after the failure. And the sketch of the construction situations of 11-meter long tunnel section prior to failure. So the left side of the tunnel was almost complete. The valve had already been underpinned on the left side, and worker located on the left of the tunnel was welding steel bars between successive steel posts to improve their lateral stability. So the right buttresses was in place supporting the semicircular head steel set. So it seems like the correction phase was perfectly in good positions, not having any kind of failure or not indicates any sign of the failure signage how was started. But in details, in the morning of June 26, 1991, a team of workers began to excavate the right buttresses in order to underpin the bulb. It seems they started work on the far right corner of the tunnel, just touching the vertical front. And a big full loader and a wheel front loader were moved into the working area to assist the team. So the failure occurred immediately after the workers had excavated 2 or 3 meters of the right buttresses. So they later declared that the valve collapsed on them, and they managed to escape protected by machine. However, the weather working on the stabilization of steel posts on the left side of the tunnel was killed by the roof collapse. So the tunnel failure left a 12-meter high sinkhole or cavern or approximately cylindrical shape. So the consequences or tunnel excavation failure resulted in what we call it as a cavern. So this is the again the schematic diagram final excavation before failure, and this is after fail. So it happened that on top of the tunnel roof, what we call it as a valve, that's having some kind of the big hole sinkhole. So they tried to investigate what was causes to the failure, and when they did on the back analysis, and there are 2 or 3 some causes that related to the failure. And before we go to that one, it stated that okay, the approximate diameter of the hole at the street level was 7 meter, and the dimension of the base of the failed tunnel section were around 8 times 11 meter. So from the observation in the report issued by the fire department, say that the collapse did not reach the street level. However, the collapse valve was only loaded by a relatively thin layer of soil whose thickness was estimated visually as being around 1 meter. Further observations after the second and definitive collapse, once the debris and machine were removed, provided additional details. So the good thing is that the failures not reached to the some place or some section that can be reached by public. So that's a good thing. And then from the final observations, it showed that the finished tunnel as it could be observed from the open cavern. So the exposed soil had a significantly clay and silt content. So this kind of soil type were found during the day or during the collapse of tunnel. So because on at the first beginning they did on the bore log SPR 2 and 5 uh, randomly show that the presence of clay and silt content. And the picture also showed that the overbreak occurred during the valve excavation. So they were filled by concrete. So this another causes that triggering to the collapse of tunnel excavations. So when the collapse section was excavated, bury steel set, which once supported by the valve, were uncovered. So the sets and the vertical steel supports had tilted towards the right buttress, and this shown by photograph. And this observation indicated that the failure was most probably preceded by a loss of support of the set resting on the right buttress. So in other words, the instability of the right soil buttress loaded by the valve was at the origin of the catastrophic failure. So in final conclusions, they conclude there are two main reasons that triggering to the tunnel failure. The first one is due to the loss of support that resting on the right buttress, and also the other sides is the loaded by the valve. So when they are doing the analysis, back analysis, they are tackling the issue on these two causes. Okay, before they can start doing the analyzing or back analysis to support their hypothesis and assumptions, the failure occurred due to the two reasons. So first, they analyze the case according to these informations. For example, if you have a plan view of the failure, so this is the regions of the collapse contour. So they proceed as follow. The stability conditions of the cavern will be formulated with the aim of deriving average strength parameters for the soil. And then the second one, the actual soil loads against the valve, knowing that the right support was yielding, will be investigated by considering arching effects in the soil. And the final one, the failure conditions of the right side buttress loaded by the valve will be examined. So in this case, this we can categorize as a soil structure interaction problem, because it's not only involved on the soil supported the in not just involved on the soil supported on the soil support tunnel itself, but it also having some soil mechanisms, the vertical stresses, the lateral stresses uh, around the tunnel itself, and then the structure loading on that acting to the soil, and finally the effect of the soil buttresses. So they are trying to analyze according to these three conditions. In order to have the final conclusions on their assumptions or hypotheses, they did on the back analysis, firstly to check on stability of the cavern. So the field tunnel sections with the wide 8.4 and long 11 meter, approximately by half sphere, 5 meter in radius are. The center is located at 10.5 below the ground surface. So the tunnel collapse created a cavern reaching the surface, having approximate truncated conical shape. So the upper contour of this truncated cone is shown in the figure 7.10. So let us go to the 7.10. Okay, this is the 7.10. So from the 7.10, they try to derive the problems. So the conditions leading to instability of this mass of soil on top of the fair tunnel will be used to characterize the soil strength, which could be approximated by C-Moore column failure criterion. So the good thing is that they assume that the soil fail in accordance to the Moore column failure criterion in the unsaturated condition, which no distinction between effective and total strength parameters will be made. So it says that you assume as a total stress analysis, it is enough just to get what are the strength parameters during the failure occur. So in order to get the set of strength parameters, they need to do back analysis by assumption that the soil fail in accordance to the Moore column failure criterion. Okay, the Moore column failure criterion only requires 5 parameters. For the first one, for example, cohesion, the strength of the soil, and then the internal friction angle, the Young modulus of the soil, Poisson ratio, and finally is a dilatancy angle. The dilatancy angle will explain to you the plastic conditions of the material that particularly refer to soil at the critical state or at the failure region. So a drain mechanism will be assumed and stability condition will be solved by means of the upper bound theorem of plasticity. In order to comply with the associativity rule of the plastic theorem, the dilatancy angle of internal failure surface is given by the friction angle. This is what it says that to assume as the associated flow rule, we're going to take the dilatancy angle, one of the parameters in the Moore column method will be equal to the internal friction angle. For example, if your friction angle is 30 degree, so the dilatancy angle will be equal to 30 degree. However, if the soil behave differently with a different value of dilatancy angle, so we call it as a non-associated flow rule. So the associated flow rule that brings to you the plastic conditions of the material field. Okay, since they are using the upper bound theorem of plasticity, so there will be a kinematically admissible mechanism. So the mobilized failure cone must have a vertex angle of 2, 3. In the figure 7.12 shown to you, the motion of the cone is vertical and the cone sphere interaction defined as spherical dome, which limits the cone in its lower part, meaning that they just only covered at the upper part. So the radius of the circle intersections R1, where is the R1? So R1 here will be controlled by angle alpha. If you look at the figure 712 on the left side, and in fact, the geometry of the family of cone considered in the optimization processor will be characterized by the angle alpha. So on this particular figures 712A, B is actually they are trying to derive the problems in approximate kinematic solutions. So the apex of the cone may be located inside the soil or above the upper surface depending on the friction's angle. So what it says that assuming that the failure occurred here on top of it, so by having the semispheral and semicone on this image of the cavern failure and the cone vertex inside the soil, so they derive from the figure 712 into this kind of the formula beginning from 7.1 to the 7.1a to the final 7.1e. So what actually they are trying to find what is the radius R1 and also R2. So the R1 is if the converted vertex remain inside the soil, and the figure B is the conditions where the convertex above the ground surface. So they are conditions before and after. If the condition of the failure the vertex inside the soil profile, or if the vertex above the ground surface. By having these two conditions, they are deriving, we have R1 is equal to R sine alpha, meanwhile R2 is a maximum, limits 0, R1 minus H tangent phi. And from the equations, says that stated the R is the radius of the sphere where R equal to 5. RE is the tunnel cover, which is 5.50. H is the height of the cone apex, and H max define the height of the truncated conical volume. R2 is the radius of the upper face of the truncated cone in the second case, and G is the auxiliary variables. So the volume V and outer lateral surface A of the cone are given by, so A, as stated in the equation 7.2b as here. So A, the area is pi R times R1 plus R2 times H over cos phi. So what's the meaning of this one? Because they are trying to find the relation between the soil strength with the parameters governed by the field tunnel excavated. So the tunnel excavation, our main role here is the tunnel excavated failure. So from the geometry of the failure of the tunnel itself, the deriving to have kind relation with the soil strength C. And when they started to derive by having the virtual vertical displacement rate under the rate of work performed by external forces and the internal distributions of work on the failure surface, finally they found that the work performed W external is equal to the volume of the soil times with the unit weight of soil times with the depth. So in the drain sharing, the energy dissipation per unit area is given by C times with delta T. And delta T is the displacement component in the directions of the failure surface. So all these are referred from the theory produced by Atkinson 1981. Since the displacement component delta T is equal to delta cos phi, therefore the energy dissipation W internal is equal to C times LA times delta cos phi. So the condition W external, if we assume as equilibrium W external equal to W internal, that leads to explicit expression for C is equal to V times gamma over A cos phi. So V and A are functions of alpha, which having from this equation 7.2A and also 7.2B. Okay, the next one, after they got the equation, they try to plot in just showing how the three coefficients for these particular cases are related to the alpha by having different frictions angles. So it shows that for a given value of phi, equation 7.5 provide value of C, which depends on the geometry defined by alpha that led to the collapse. So if you are looking for the maximum value of C in terms of the alpha, the required for the equilibrium in order to find the upper bound that hopefully will be close to the true coefficient. So originally, if you have first angle as a 22 degree, that's the highest C. And then when the frictions increase, you will have lowest or maximum coefficient that lower than 22 degree when you have the C equal to 18, for example. So this graph was plotted according to the equation that obtained from 7.5. Okay, the finding of the maximum of C dependent to the alpha, it shows that the calculated values for C is varying of alpha, and the selected range of phi around 22 to 30 only cover for the expected friction angles of the excavated soil. So the calculated coefficient values for 14 to 18 kPa are quite low, but consistent with the instability suffered during the head excavations. If you have the phi equal to 28 degrees, that is a reasonable value. For the critical value of alpha is around 50 degrees. So the vertical coefficient leading to strict equilibrium, which C equal to 15.4 kPa. So then equation 7.1 predict a critical failure cone having a vertex inside the ground but close to the surface. So by first assumptions, by deriving the geometry of the fill tunnel and related to the coefficients, they found that the critical value of coefficient during the failure. Okay, let us now consider the problem of determining the soil load on the tunnel valve. So it just solved for the P and also for the C. So the next cause is due to the arching effects and loads on the tunnel valve. Tunnel valve is some kind of the arch shape. So on top of this one. So this figure 7.4 shows arcing effect induced by a yielding support. So the theory adopted theoretical soil mechanics from Terzaghi 1943, and he developed an altering theory to estimate the loads exerted by the soil on the tunnel valve. So the classical concept involved the yielding of part of the lower horizontal support of a mass of soil. So the downward motion of the soil is opposed by shear forces developed in surface AB. This is the AB and also the CD. So this is the soil mass. So the yielding support in the tunnel valve. So when the valve settles, the soil above will be partially supported by internal shearing. So this load transfer mechanism reduces the vertical load applied to the valve. If principal stresses are considered, the major principal stresses tend to form discharge arches in the vicinity of the yielding support. So these internal arches are also a convenient mechanical interpretations of the phenomenon and help to explain the increase in normal stress on both sides of the yielding support. So if you take it this one as a soil element and considering there's some any other stresses involved such as major principal stresses and then the shearing resistance. So how this actually will be given some additional loads effect to the tunnel arch or tunnel valve. Okay, consider we go to image 7.15. If you consider 7.15 here, this is one element of the saw supporting a circular shape and radius r. This is the radius r at the bottom of the cylinder. The thickness of the saw is a h, and for simplicity, the resistance shearing will be assumed to act on the cylindrical surface of radius r. Consider the vertical equilibrium of the thickness dz located at the depth z. So if you have this z, so by small element of the soil as a dz, so we can have the additional vertical stresses, the increment of the vertical stresses as a d, that d sigma v. So it started by deriving the load effect on the valve as we can see from the equation 7.6. So the 7.6 equations actually related how the stresses with the soil element at the arching or at the valve given to the stresses or given to the additional stress at the part of the tunnel itself. So this one, if you look at from this equation 7.6 is actually from the explanations at the part of image or figure 7.15, and considered also the K is the coefficients of earth pressure. So the cylindrical cone of the structure or inside the soil mass, the mobilized cylindrical soil body above a circular yielding base, and the arching effects can be seen from this one. What it says that the deriving from the equation 7.6, they come up with the vertical stress at the particular sections fail of the tunnel itself. So it says that it given the vertical stress at the particular point from the 7.6 equations, the vertical stress is equal to the R times gamma minus 2C over R over 2K tangent phi times 1 minus exponent 2KZ over R tangent phi. So what is the K? K is the coefficient of the earth's pressure. So as I said earlier, the soil, when the soil is functioned to retain any kind of the movement, and if you have any kind of the structure to retain soil movement, that will be a condition, the stress in the passive, active, and at the rest state. For this condition, it's assumed that the lateral stress, and also the parameter or coefficient that control to the lateral stress with the vertical stress, which is K, is the constant or at the rest conditions. But somehow the K is also depending to the phi value, the internal frictions of the soil. Okay, the equation 7.7 represented by 7.15 for the three values of the at-rest pressure coefficient in range 0.8, 1, and 1.2 for a set of parameters which characterize the arching conditions developed above the yielding valve with the radius 5 meter. Unit weight of soil is 20 kilonewton per cube meter. Cohesion is at 15.4 and phi 28 degree. So the C and phi value are taken from the previous analysis at the first assumption, the soil parameters at the failure state. So the strength parameters were back calculated in the previous section from the global collapse observed a few hours after the initial failure of the valve took place. Okay, Tazaki reported instead indicates that the value of K increased from about 1 immediately above the center line of the yielding strip, and he considered in two-dimensional problem, so the maximum around 1.5 at elevation of 2R above the strip. So the value K 1.2 seems reasonable in the case. The solution of K 1.2 yields a vertical stress of 42.6 kPa for a depth below the surface of around 6 meters. So it's not reasonable to pinpoint stress values at larger depth because the presence of the valve implies a weak defect. So which would lead to smaller sigma V values that those represented in figure 716. Tazaki also mentioned if the depth of the yielding support sag increased, the yielding of the lower support is not noticed in the upper layer. So he specified that arching effect disappeared at height in excess of 5R above the resisting mechanism of the failed portions of the tunnel is complicated structurally speaking. The valve was continuously across the limit between the tunnel already finished. So, in the figure 17, the fail, it from this figure 17. Okay, this one is a figure 17. This is the schematic of the collapse length. Then soil buttresses for the conditions of the tunnel. So before we can go that particular thing, this is the value they got after they have relation the sigma v, having kind of the k and also the depth. So you can see here by different k from 0.8, 1 and 1.2. So it shows that the 0.8 will give highest vertical stress sigma v. So this is proven from their equations. At what depth? So you can see if you go deeper around 20 meter, so the maximum sigma v for the k equal to 0.8 is more than the k 1.2. So the valve actually in three-dimensional problem, but the Tazaki derived the equation according to the two-dimensional problem. So you Okay, from the figure 716, vertical stresses over a circular yielding base. So the Terzaghi and also from the case study back analysis, they took the value K equal to 1.2 at the effective vertical stress equal to 42.6 due to the reasons that if not reasonable to have a value that larger the depth because that presence of the valve implies a weak defect. And also, if the depth of the yielding support Z increases, the yielding of the lower support is not noticed in the upper layers. So that's why if you can see from the K value in range 0.8 to 1.2, so they just took the value K equal to 0.12 at the effective vertical stress equal to 46.2 kPa. So it is reasonable to accept that during the yielding of the fair section, some of the soil load exerted against the valve, and if it is reduced by arching effect, would be shared by the stable tunnels. So the valve are known to develop strong three-dimensional interactions against the deformations. So if you have some further analysis in three-dimensional, so it more better. Meanwhile, also, the geostatic indicates from the figure 17 where the proposed distribution vertical stresses from the Terzaghi analysis, the soil develops the full geostatic stress profile above the 5R limit mentioned and the stress decreases until it eventually joins the predictions of equation 7.7. So the equation for 7.7 is actually the determination effective vertical stress having the relation to the coefficients of earth pressure, unit weight of the soil, the radius of the arch or the radius of the tunnel. And from here itself, mentioned that the geostatic conditions, if you have the yielding support at these particular sections, and this is the R, and why it is reasonable to take the value at 46.2 as mentioned just now at the K equal 1.2 is due to the reasons. So if it is exceed 5R, so it is not reasonable. So that's why they just take it the value according to this dash line that equal to the equation 7.7 in order to determine what is the effective vertical stress during the failure. Okay, if half of the average vertical stress was transferred to the stable tunnel, the valve would have received only small pressure estimated around 21.3 kPa, which roughly correspond to the observations of the firemen in the sense that a layer of the soil whose thickness was estimated 1 meter accompanied the valve during its fall. So we can see that the effective vertical stress as part of the additional loads that acting on the top tunnel has triggered to the tunnel collapse. So the tunnel's collapse is mentioned if it's only carried by half from the 42.6 kPa, that will be less stresses. So now, as what they assume, according to three causes, almost close to the final one they found on the site. So the next study, they try to back analyze on the buttress failure. So the foundation, the valve on top of the buttress, okay, the valve subjected to vertical stress is resting on the sloping buttress, which is about to be excavated in order to underpin the steel set. So this is the image mentioned from the statement just now. So this is the point buttress, and then this is the vertical load on forces T, and here's some of the forces that exerted around the soil. So we have the soil weight W, we also have the normal force, and we have also the shear force. So it's like having simple equilibrium equations between the total force in vertical equal to total force in horizontal. So the equilibrium vertical directions applied to the quarter of the tube, it gives in the equation 7.8 as shown here. T equal to sigma v times r, and the equilibrium of which ABC in vertical and horizontal directions lead to the T plus W equal to N cos beta plus sin S sin beta. So the forces left equal to the forces right. So the shear force S is expressed in terms of the modulus coefficient. C modulus is equal to C over SF, and friction tangent modulus equal to tangent phi over SF, where SF is the safety factor. So the S is the shear force is equal to N tangent phi modulus plus C modulus L, and the L is the length of the arc. Where is the L? So this is the L. So the solution 7.9 and 7.2, 7.9 and 7.10 leads to the following equations. So since they want to determine stability of the buttress on the tunnel itself, so they found that the shear force on from the buttress effect is equal to N tangent phi modulus plus C modulus L over N tangent phi. So it means that the shear force is equal to the shear strength over to the shear stress, or resisting force over to the disturbing force. So once you get the resisting force to the disturbing force, you can determine the value of factor of safety. So the N is T plus W over cos beta plus tangent beta sin beta. So the equation 711 being plotted in the figure 720 shows that the increasing value of T for the buttress dimensions left after the excavations of the lower bench section of the tunnel. So, um, so for the unit soil of 20 kilonewton per cube meter, so it is correspond that for the pair shear strength parameters V 28 degree and C 15.4 is indicate these positions of A. So the actual load per unit length acting on the top of the buttress may be approximated by equation 7.8. The equation implies an infinite extent of the valve in the longitudinal directions. However, the field length of 11 meter long had a common valve with the remaining part of the tunnel already built. So in other words, the continuity of the valve provided an additional support which difficult to take into account without a specific structural analysis, which in three-dimensional. So the figure 718, so explain to you what and how this is related to the structural structural analysis in the three-dimensional. But we are now focusing on part of the geometrical on the geotechnical view of point. So from here, what we can say that for the safety factor at 1, this is the load, or this is the point A. So the factor of safety decreasing by increasing of the load T. So this one, remember we want to find what is the safety factor for the tunnel, right? Due to the buttress effect. So you can have that when you increase the loads, so the factor of safety decreasing. So the intersection for safety factor 1 with kind of the decreasing of load that meets at the point A. So here, the safety factor equal to 1, we can say that the soil near to the unstable condition. If you have the SF or FS more than 1, that is the stable point. The point A indicates the state before starting the work in the morning of June 26. So actually, it shows that the sign of the failure close to occur. So when you have this kind of back analysis, or initially doing on this part of the analysis for sector safety or for stability, maybe we can predict but not accurate, because the real condition may also affect by the current situation or current environment conditions. Because this is back analysis was done by few assumptions. For example, total stress analysis without the saturations, without the water table effect. But somehow, when we are dealing with the real conditions, one thing that we could not control is the pore water pressure effect. So the pore water pressure effect might give you very complex analysis that will be related to the effective stress analysis. So you have to consider also the saturated condition, unsaturated condition. So in this case study, they did on the back analysis with the limited assumptions. For example, as what you can have for for this. Okay, in other words, if you have both very effective in supporting structures, but did not have any longitudinal steel reinforcement, so it roughly been estimated that the contributions of the remaining of the tunnel to support loads on the final section was close to completions. Okay, figure 721, telling you that when they did on the load increment, for example, here we can have that once the load increment increase with the excavated length of the buttresses. So when you increase the length of the buttress, that will be also increase the load. So the figure 721 just now indicates at the time of starting the work in the morning, so the safety factor against failure of the soil buttress was low. Not also that without any valve effect, the failure could have taken place at an early date. So when they did on the analysis, they found out the average load on the soil buttress T is equal to 106 kilonewton. 106 kilonewton as at point A. So the loads increment, when you increase the buttress length, that also increase the load increment. So the effect will be having some kind of from the verb itself. So consider the effect of opening lateral niche to underpin the steel set. So the length of the bench around 11 meter would be progressively produced if the sample calculation is made. So the buttress depends on the length at the supporting valve. So the following expression is calculated for increment of load delta T over the initial value. So the delta T from this case study is equal to EL over 11 minus EL. So the 11 is taking from the length of the collapsed tunnel, and this assumption made according to the failure. And the excavation length of 2, 3, and 4 meter results in load increment of 22, 37, and 57% over the initial value. So the load increment implies a reduction in safety factor, which shown in the figure 720. For excavated length of 1.5 to 2 meter, the safety factor is already 1 and the failure is imminent. So the evolution of safety factor can be seen also from the figure 7.22. So from the discussion, This question is actually explained to you the process of construction procedure. But first of all, the important part is the development of large cavern lighting at the surface was the starting point of the analysis. So the soil strength, which explained this failure, was used in the subsequent examination into the reason for the failure. So since the soil involved unsaturated, a drain analysis was performed. So the upper bound theorem of plasticity offered a convenient tool to handle the approximate conical shape of the failure. So from the back analysis, the combination of C and phi parameters leading to the failure. So the combination C and phi, just now we had phi around 28 degree and the C is equal to, what is the C value just now? P is 28 degree and the C is 15.4. By having this set of the critical set of the strength parameters during the at the failure occurred, so they did analysis to the extent part of the arching effect and also additional load due to the buttress. So this difficulty is more apparent than the real because alternative C and tangent phi pairs provide similar result in subsequent calculation. The other one is that the analysis of the failure right buttress indicate that the failure conditions were achieved for a relative minor proportion of the expected geostatic load against the bomb. So this has been attributed to arching effect, meaning that when you are proposing for tunnel excavations, you have to include also the arch of the constructions, where point need to be started first and which would be at the last part of the tunnel excavation section. So for tunnel shallow, for shallow tunnel, the arching may be very effective reducing the actual surcharge. So the classic Sasaki theory of soil arching applied to a yielding cylinder has proved useful to approximate arching in this case. So the recent works, according to the finite element elastoplastic, we supported of the Tazagi analysis. So the simplification need to be done to accommodate the real geometry to an able case, but the reductions in apparent loading attributed to arching is consistent with the final step of the analysis. So the instability of the right buttress under valve loading were shown and indicate in the analysis. So the simple calculation procedure by limit equilibrium explain the failure. So the most sophisticated calculation procedure are probably of doubtful relevance in the case because the key aspect of the entire analysis is the correct selections of the strength parameter at the first stage and the arching effect in the second stage. So again, because this is a soil structure interaction problem, so you need to consider from different geotechnical aspect as well the structural aspect. The geotechnical aspect, of course, the soil parameter set, and the structural aspect is the arching effect as well, the additional load from the right buttress. So what are the mitigation measures? Of course, the first one is to adopt the correct or appropriate procedure in the excavation. For example, the construction method, so-called Belgian method. So the Belgian method is actually showing to you by this step from the A, B, C, D, E, F, and E, also G. So you can see how it was started. It was started at the middle sections in the arch of the tunnel and extending to the B with the underpinning process, with the reinforcement. And then in the section C, uh, so in the section C, you can see some the arch is supported by ribs on the frontal post, extending from a central unexcavated mass of soil and the concrete arch already built, and then the timber or any steel planks driven by vibrating hammers to support the exposed soil between the ribs. And the next process is the central unexcavated soil buttress is maintained to stabilize the front of the tunnel. And then the valve arch is then underpinned by relatively narrow excavation or pits which allow the construction of sidewall in order to transfer the valve load towards the level of the inverts that indicates for figure EF. And finally, the process ends when the entire section is excavated and the curve invert or if necessary. So the entire process in the labor intensive and requires specialized focus. Of course, the tunnel excavation is not cheap cost. It requires skilled workers. It requires full understanding of the construction stages, and the safety precautions is also important. Okay, the other one from here, besides the bench excavations, is also to include the last one is that a more careful underpinning operation excavating lateral openings of a smaller length could have prevented the failure. So, even better procedure to advance the excavations of the lower half of the tunnel at a slower rate, avoiding the long central corridor. So, this would enhance three-dimensional effects and help maintaining the stability of the valve during the installations of HDB poles and the construction of the side walls. So they are related back to the construction methods. So these are the some mitigation measures. If you understand the methods of tunnel excavation, that will be okay. You follow from one step to the last step. What are the lessons learned we can have from this case study of uh, ball of this Borràs Square in Spain? The first one is that the frequent source of the tunnel failures or the bench excavations. Okay, the other one is the benefit of arching. The benefit of arching, for example, the tunnel designer should aware the need to ensure stability of the foundations of the valve during the bench excavation. So if you remember just now, the bench excavation for this case study was started in the second phase. So it would not dare reducing the overburden stress below its nominal value. So the reason is the low cover to diameter ratio. So the case indicates that even for these shallow tunnels, arching helps to increase safety factor. If it was not capable, however, ensuring the adequate safety in this case, because other design and construction specifications reduce the safety factor. So some other reasons need to be considered to increase the safety factor of the structure. The other lesson learned is strength parameters from back analysis of the failure. So the back analysis of stability failures provide good estimations of the field strength. The pore water pressures are typically difficult in drain calculations because they are often unknown at the time of the failure. So in the case described, the soil was not saturated and the analysis was performed in total stresses. So no attempts were made to directly introduce the suction effects because of a lack data. So this is good about back analysis. Some, as I said, if you want to start doing the back analysis, you have to provide a set of assumptions. What are the assumptions you're going to make in your analysis? Are you going to consider as a total stress analysis or effective stress analysis? If you consider as a total stress analysis, but having the effective strength parameters, and if you are adopted for the shear strength reduction techniques, what are the best construction stages can be followed or can be used in your analysis, in the numerical analysis, for example. So last but not least, the structural strength of support is generally not an issue in shallow tunneling. For example, here, if you have the shallow tunnel, the bending moments, normal and shear force in steel set were far from reaching critical conditions in this case. So to check was not included here, but necessary to discard a structural tunnel failure. So this is generally the case in shallow tunnels. The risks in shallow tunneling are associated with the soil instability, meaning that since we have a shallow tunneling, so actually, we can ignore the effect of the structural stability. We can only focus on the soil stability. So when you have when you have concerning, or if you have concern in the soil stability, you need to check on the soil strength critical parameters and do the back analysis to get the sets of parameter contribute to the soil failure. So here for the Borràs tunnel excavation collapse in Spain, it was occurred due to the, I think my personal opinion is due to the soil strength parameters, because after the failure occurred, they found that the soil at the particular area consists of clay and silt, which couldn't easily seen from the bore log from SPR2 and SPR1. The other reasons is due to the load increment or additional vertical stress acting on the arch or at the valve of the tunnel itself. Not to forget the buttress effect. Okay, that's my personal opinion regarding to this kind of the tunnel excavation failure. Do you have any kind or any suggestions or any question you would like to ask? Next week will be new chapter 5 on landslide.
So doktor, kalau ada groundwater table, kita kena buat apa pula doktor?
Kalau you ada groundwater table first you can analyse the effect saturated dengan unsaturated conditions. Kemudian bila dia adopt advanced theory nowadays more column model tu dah tak relevant untuk kita analyse problem yang related to groundwater table effect. Maknanya you kena tahu conditions mana zone yang dia unsaturated, mana zone dia saturated. Bila dia zone saturated, dia punya shear strength bukan lagi shear strength tau sama dengan V plus sigma N tangent V. Itu yang conventionally more column produce. More column produce for failure criterion. Tapi bila you dah ada effect of the saturated, unsaturated, pore water table effect, water pressure semua, dia dah extended the more column equation dengan considered the unsaturated formula. For example, biasa kita tahu pore water pressure kan, sekarang ni dia ada pore air pressure pula. So formula tu dia dah masuk satu lagi elemen baru. Elemen baru tu dia akan modify the strength of the soil. So bila contohlah you nak analyse this kind of problem menggunakan advanced model, advanced constitutive model, more column tu bukan lagi best model to describe the soil behaviour. So you kena pakailah, for example, Chem Clay model ataupun modified Chem Clay or any advanced model that tackle all these kind parameters tu. Macam water pressure effect, air pressure effect. Tapi bila banyak parameters, dia akan ada some issue macam mana nak dapat nilai dia. Data ni nak ambil daripada what kind of testing that bring to this kind of the input data. So benda-benda itulah. Kalau sharing stage, draining stage, berapa nilai for water pressure dia, U dia berapa, the access for water pressure, semua-semua tu kena ambil kira lah balik dia punya analysis. So the analysis will be not easiest by hand calculations lah. So bila dah complex macam ni, dia kena pakai numerical software.
Oh.
Untuk topik landslide nanti, kita akan ada technical talk from the industrial advisor lah. So dalam week 13 lah. Yang tu pun nanti rasanya Dr. Ong Kat Shin akan share lah dalam group. So dia ambil waktu yang sama lah, waktu kelas saja. So dia tak kacau waktu-waktu lain lah, session yang lain kan. Kelas biasa minggu 13, 8 malam lah akan ada industrial talk, technical talk untuk topik landslide tu. So landslide common failure kan occur in Malaysia due to the natural disaster or any kind of the reason, right? So that will be interesting topic next week and next following weeks. So I hope that kalau kata masih tercari-cari projek nak buat kan, landslide tu pun boleh jugalah untuk you jadikan sebagai projek you lah kan. Kerana excavation ni sebenarnya agak susah lah, sebab kalau kat Malaysia contoh yang tanah excavation ni Selalunya kita akan buat tunnel ni dekat kawasan mana? Apa contoh paling close dengan kita? Siapa pernah ingat-ingat lagi lah?
MRT. Projek MRT.
Projek MRT. Okay, tapi itu underground kan? Underground tunnel kan? Boleh lah
Underground.
consider juga underground tunnel. So, bila underground tunnel dengan tunnel yang ground lah kan, contohnya terowong menora tu, itu dia melibatkan rock formations kan, nak kena tahu weakness plane dekat mana. So kita nak buat proses extruding tu, kita tahu dah weakness plane kita kena void, atau bila you dah faham weakness plane dia, kita tahu lah nak starting point kat mana. That's why dekat dalam mitigation measures tadi ni ataupun lesson learned part of the discussion, they said that on the classical method of construction, bila you follow that one, it should be okay. Kalau kata MRT underground tunnel, that's also similar problem. Contohnya kalau you have a project in KL, Kuala Lumpur for example, the most soil or rock formations in KL adalah Canning Hill formations. Canning Hill formations are originated from the limestone. So talking about limestone ni, dia banyak pores, so banyak ruang-ruang kosong kan. So bila banyak ruang kosong cavity ni, they will be talking about low strength. So what are the best method constructions you are going to adopt while in the construction stages? I mean that the construction stages, we're not taking straight as well 111 ataupun one straight length. They will be take it stage by stage kan. Contohnya kalau tunnel you panjang dalam 10 meter kan. So kita tak terus extrude boring tu dengan 10 meter. Kita akan bore or core by length lah kan, tengok ada tak problem dia. So ada beberapa stage yang kita perlu tengok. Mostly formation yang jenis limestone ni very 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 critical and difficult to handle with because kita tak tahu kan nanti depan tu ada cavity ke tidak. Kalau ada cavity, sebelum nak buat dia punya coring tu, sebelum nak construct tu, kita kena masukkan concrete filling dulu. Bila dia dah kuat tu baru kita buat excavation. So these are the things yang bila cakap skill worker in this particular section area, kita agak kurang lah. That's why lah bila kita ada projek infrastruktur yang underground ke, apa ni, ground surface ke, yang MRT kat atas semua tu kan, kita perlukan expert luar. And then equipment dia, machinery, jentera-jentera dia semua costly. That's why the project tu mahal. That's why infrastruktur project ni very costly, dan return to public pun dia charge dengan extra extra fee lah kan, charge tiket pun mahal kan. Padahal in purposely tujuan dia buat infrastruktur MRT, LRT tu to reduce traffic volume, to provide a good facilities to public in transportation. Maknanya kurang pakai kereta sendiri, guna public transport. Tapi bila dah farenya mahal, tambang dia mahal, so semua orang prefer guna personal or vehicle car. So I'm not sure lah apa yang they try to solve the problem in KL. Jam masih lagi berlaku. So banjir masih lagi berlaku. So nothing changed. Okay. Itulah kan pendapat saya lah kan. Tapi nak ceritanya pasal tunnel excavation tu, bendanya agak kurang pakar lah dalam area tu. Kalau kita boleh perbagaikan, banyakkan generasi kita yang very interested in this particular area, should be okay lah. So some student they like on the structural engineering instead of the underground excavations engineering kan. Yang tu yang sepatutnya kita kena go in depth, and then kita ramaikan pakar-pakar kat situ. That's my opinion lah. Betul tak? Kan pakar-pakar dari JKR ke, daripada THB sendiri ke, atau Encik apa ni, Mizia ataupun Encik yang berminat lah kan, nak share your experience or your knowledge about this one. Maybe you can encourage our young generation to get involved in this area. So any more questions? So actually this topic, kalau you tengok sendiri kan, dia lebih kepada geotechnical punya knowledge lah. So tunnel excavations ni dia melibatkan geology plus dengan geotechnical. Geologi ni kalau dia melibatkan rock formations. Tadi dalam case study yang ni pun the soil profile first dia came out dengan rock parent rock. Dia identify rock ni jenis metamorphic, ada yang jenis sedimentary. So apa tujuan dia? Sebabnya dia nak tahu kalau tanah tu jenis sedimentary, maknanya layering bedding plane dia tu mungkin banyak. So bila bedding plane dia banyak tu, apa cara kita nak buat part of the construction, best construction method bila kita ada this kind of the bedding plane. Atau kalau dia tanah yang jenis granite, so maybe less problem, so less method of construction yang costly yang kita boleh ambil dalam kita punya kerja-kerja tu kan. So that's the important, we talking about the tanah excavation ke underground excavation, you kena tahu the formations of the originality of soil ke rock ke macam mana dia. Dia punya karakteristik tu apa. And then parameter dia apa. Tu yang penting lah. So, bila parent rock ni metamorphic lain, sedimentary lain, igneous lain, the formation itself pun berbeza in terms of the strength. So, the granite, igneous rock lagi kuat kan sebab dia form from the lava. And then melalui weathering process, dia form into different type of the granite and then different group of rock itself. Same to the metamorphic and sedimentary rock. So, benda-benda ni penting bila talking about this kind of the construction activities yang melibatkan rock ke, yang melibatkan soil, so kita perlukan ada expert geologist, and then kita perlukan kalau kawasan tu kita nak buat tanda kawasan baru yang orang tak explore lagi kan, mungkin kita perlukan surveyor. So all these experts are gathered in one team, in one project. So very good lah kalau, that's why I say lah, baguslah kan kalau kita boleh sit together, kita expand this knowledge among Malaysian expertise ni untuk sama-sama lah untuk majukan negara. Okay, ada soalan lain sebelum kita habis our class tonight? My personally would like to say thank you to every one of you joining these online sessions for around 7 weeks. And my personally would like to ask your forgiveness is if along this class some sound of disturbance, ada yang benda yang mungkin tak sampai ke your own understanding or your own